This is Neil Patwari. This is ESE 471. In this segment, I'm going to answer the question, why is received noise additive, uncorrelated, and Gaussian? And I had said in a previous example that when I send symbol I at the receiver, the output of the downsampler for one basis function looks like this, for some Gaussian random variable w. But I didn't say why this was. This segment justifies why this is. And further, when we have k basis functions, we get xk is equal to a sub I comma k plus wk for the kth basis function. This segment talks about how the noise values on the multiple basis functions are related to each other. In particular, that they turn out to be uncorrelated. And knowing this will be critical in building an optimal detector when we have multiple symbols and we have multiple basis functions. We'll start in the continuous time domain for the case that the signal that we measure is a sum of the desired signal and thermal noise. So this model says that the received signal is our desired signal plus thermal noise. And there can certainly be interference in communication systems, but we're going to assume for now that we've avoided the interference so that we only have the thermal noise. And the noise Wt is, as we justify in the next video, it has this mean function of 0, and it has an autocorrelation function, Rw of tau, equal to n naught over 2 times an impulse function with tau as its argument. And we send R of t into a match filter, and then we sample that n multiples of t sub s. And out of that we get an integral of R of t multiplied by phi k of t dt, integrated over all time. And what we're going to be interested in is this value, which we're going to call xk. And xk is going to be equal to the desired transmitted signal, a sub I comma k. That's the amplitude of the kth basis function sent for transmitted symbol I, plus some noise, wk. What are the properties of wk? So because xk is this integral, I can then plug in the model that R of t is equal to st plus wt. And thus I'm going to have two integrals. This second integral is what I'm going to call w of k. Okay, and we're going to study the statistics of what this is because it's hard to talk about what exactly it is because it's got a random process in here, w of t, influencing the outcome of the integral. This signal, the s of t, remember, is some amplitude ai of k multiplied by phi k of t plus, other amplitudes multiplying by other basis functions. And these other basis functions, when I integrate over all time, those are going to go to 0. And when I multiply this one and I get ai comma k multiplied by this integral of phi k of t multiplied by phi k of t, this integral is going to give me 1. So in other words, I'm going to get ai comma k plus wk. Okay, and that's what I've written up here as a summary of what happens to this integral. The questions we have, first of all, what is wk? What are its properties? 1, wk is Gaussian. We know this because wk is an integral of a Gaussian random process. Any linear combination of a Gaussian random process is another Gaussian random variable. And an integral is a linear combination. It is a sum of the area underneath the curve. It is a linear combination. So because it is an integral of a Gaussian random process, wk therefore must be Gaussian. Point 2, the expected value of wk. That is what we're calling mu w of k. It's equal to 0. And here's how we're going to show that. We're going to plug it in to the formula that we just gave for wk, which is the integral of wt times phi k. Well, an expected value is an integral, It is a linear operator, so I can exchange it with the order of the integral. And the phi of k is a deterministic function. It's not random itself. So what happens when I exchange the integral with the expected value is that I get the expected value of w of t multiplied by the basis function. And because the expected value is 0, as we talked about in another segment, this whole integral is 0. So the expected value of wk is 0. It has a 0 mean. And then finally, what is the autocorrelation function for w? Okay, the covariance of wk and wl is equal to the expected value but because this mean is 0, this mean is 0, this is the expected value of wk times wl. Now we talk about the autocorrelation of noise values at different times for the continuous time process w of t, but we haven't talked about what this expected value is. And to do that, we're going to have to plug in the integral equation, the integral definition for w of k. The second integral shouldn't have the same dummy variable. If I use t in the first integral, I'm going to have to use something like tau in the second integral. And just like before, because the integrals and the expected values are linear operators, I can exchange them and just put the expected value on only the random thing, w of t and w of tau. This should be an L, because it's WL, so I should be putting in a phi sub L there. Phi sub L of tau Okay, so I've got an inner integral here, and I've got an expected value that is the autocorrelation function for the continuous time random process W. And we've shown that in our other video by using the properties of the thermal noise random process that this is the autocorrelation function. This impulse function is in the continuous time domain, so it is going to do the sifting property on this first integral, and it's going to pull out only the cases where the tau is equal to the t, because that would make this argument of the delta function 0. So the sifting property pulls out this tau and replaces it with a t. So I get out of this integral phi sub L of t and the constant n naught over 2. And then finally, by pulling the constant out and observing that this is the inner product of two basis functions, if the k is equal to L, then I get a 1. If not, I get a 0, because the inner product of two orthogonal waveforms is 0. I can write this equivalently as n naught over 2 times the discrete impulse function of k minus L. It's been a long time since I started this. This is the covariance of WK and WL. So it's saying that the covariance of two of them is 0 unless k is equal to L, in which case I have a variance term. So the variance of WK is equal to n naught over 2. It's the same as the power spectral density of noise. This is really two things. One, that the WK is 0 mean with variance n naught over 2. And two, WK and WL are uncorrelated, and because they're also Gaussian, that means they're independent. And you can apply this to say something about the measurement x sub k. It is also Gaussian. It is the sum of a constant AIK and this Gaussian WK. So it has a mean of AIK because the Gaussian random variable WK is 0 mean. And the measurement x sub k also has variance n naught over 2 because adding a constant doesn't change its variance. And finally, the set of measurements x sub k for k equals 0 to k minus 1, the set is uncorrelated. That is, all of the pairs of the random variables are independent. So the noise model for x sub k is additive, uncorrelated, and Gaussian. So all in all, we call this the additive, uncorrelated Gaussian noise model. And the AUGN model Sometimes, well, most of the times in textbooks, you'll see this called the additive white Gaussian noise model, where they're replacing uncorrelated with white in analogy to the color spectrum because white has equal parts of a wide range of light frequencies, but I would say that black and gray also are equally constant in the frequency domain. So calling it white is really arbitrary, and in general, calling things that are positive white and negative things black is a bad historical habit in English. And thus, I'm going to use the more statistically precise name for this property of uncorrelated noise. Okay, so that's everything you need to know about noise in our receiver. It's additive, uncorrelated, and Gaussian.